We have one more important case to consider when we have a molecule with multiple stereocenters, the case in which we have what's called a mesoisomer. And this is where this topic gets really hard. And I understand it gets hard, and I'm going to try to work you through this so that you can really understand and appreciate when mesoisomers exist. So let's say instead of 2,3-dibromopentane, we consider 2,3-dibromobutane. We can make one of these charts showing the four possible structures, the 2R3R, 2R3S, 2S3R, and 2S3S. And we can show the relationships between them. And most of this analysis is identical to the previous lesson. So for example, the 2R3R and the 2R3S, these are diastereomers of each other. Okay, you have inverted only one stereocenter. Similarly, the 2R3R and the 2S3S are enantiomers. Okay, if we try to line up the chains, the red balls do not line up. They are clearly mirror images, but they are non-superimposable mirror images. So the question that remains then is, what is the relationship between the 2S3R and the 2R3S? Okay, so let's look at these two. 2R3S in my left hand and the 2S3R in my right hand. If we look at these, are they mirror images of each other? Well, gee, I think they are mirror images of each other. Are they superimposable? Well, initially, you may think that they are not superimposable, but I'm going to do a little trick on you. I'm going to take this structure and rotate 180 degrees about the C2-C3 bond and put both of these into the eclipsed conformation. They're still mirror images of each other, but now if I turn one of them around, they are completely superimposable. Okay, all of the carbon atoms line up, all of the hydrogen atoms line up, and all of the bromine atoms represented by red balls line up. Okay, so instead of being enantiomers, instead of being isomers at all, they are identical. So these structures can be drawn or built as mirror images, but as I said, they are superimposable. Whenever you have this case in which you have an isomer that looks like isomers that look like they should be enantiomers but are actually one compound, the structure is called a meso compound or mesoisomer. So meso compounds have two stereocenters. These are still stereocenters by definition. They are a carbon with four different things bound to them: a bromine, a hydrogen, a methyl group, and a bromoethyl group. That doesn't change the definition that this is a stereocenter, but this compound is achiral, because remember, chiral means not superimposable on its mirror image. Since this is superimposable on its mirror image, it is achiral. So one way to think about this is if you take the structure that's labeled 2S3R, okay, so this is the bottom left structure of my corner here, and number it from right to left, and then so instead of going from left to right like we did in the last lesson, go from right to left, and evaluate R and S at carbon 2 and carbon 3, you will realize that you now, in fact, have the 2R3S. And numbering this from right to left is valid for this structure because the two ends are the same. If you tried to take 2,3-dibromopentane, the structure we looked at last time, and number it from right to left, that would violate the nomenclature rules. Okay, if you tried to number it from right to left, you would then get 3,4-dibromopentane, which is wrong. and also would not be the same name, numbering it from right to left, as it would be from left to right. Okay, so let's look at this a little more closely. I did this little trick on you called eclipsing it up. I said I put it into an eclipse conformation. Well, this is frequently going to be what you have to do if you want to be able to recognize mesoisomers. The little nomenclature trick on the last slide works, but mesoisomers have a plane of symmetry perpendicular to the main chain. And that plane of symmetry will frequently only be obvious if the molecule is drawn in the eclipsed conformation, which is the same conformation I had to put it into when I superimposed them. Okay, so drawn here is the 2R3S, the mesoisomer, and it does not look like it has a plane of symmetry just looking at it like this. One of the bromines is coming towards you, the other bromine is going back away from you. But you have to remember, looking at the main chain, one methyl's going down, one methyl's going up on the end. So what you have to do is rotate this 180 degrees about the C2-C3 bond until you are in the eclipsed conformation, and now the plane of symmetry becomes evident in the drawing as well as in the model. Okay, I could do the same thing starting from the 2s3r structure. Rotate the same carbon, rotate carbon 3 into the, so now that both of the bromines are going away from you, into the eclipsed conformation, and that plane of symmetry is still evident. Now note, if I took the chiral 2r3r and try to eclipse that one up, we now do not have a plane of symmetry, because when you put it into the eclipsed conformation, one of the bromines is coming out towards you and the other bromine is coming back away from you. So it does not have an eclipsed, it does not have a mirror plane, even when it is eclipsed. And similarly, these, if we take both the 2R3R and the 2S3S, the ones that really and truly are enantiomers of each other, even if you have them in the eclipsed conformation, these two structures are not superimposable. So they really and truly are enantiomers, whereas the other isomer, the 2R3S/2S3R, is a single structure and it's a meso compound. So as a result, when you have a meso compound, even though there are 2 stereocenters in this molecule, there are only 3 stereoisomers instead of 4. And one more example of a meso compound would be 2,4-dibromopentane instead of 2,3-dibromopentane. And in this case, the plane of symmetry is going through the central carbon atom instead of going through a carbon-carbon bond. And furthermore, in this structure where the 2 stereocenters are separated by a central carbon and the plane of symmetry is going through that central carbon, the plane of symmetry is obvious even in the staggered conformation. Okay, so meso compounds are not the easiest things in the world to see, and students often get stressed, am I going to find the meso compound? Is it a meso compound? But if you just look at these rules, if you use your models, eclipse them up, and look for planes of symmetry in the way they're drawn, as well as looking at the nomenclature trick, is it the same if I number it from right to left versus left to right, you will soon become pretty proficient at identifying meso compounds.